In this video, we're going to introduce logarithmic functions. Logarithms effectively are the inverse functions of their corresponding exponential function. Let's start with an example in depth, and then we'll summarize for arbitrary exponential functions. For this first example, I'm going to take f of x to be the base 2 exponential function, 2 to the x. We're going to draw a graph of it, label some points on it, and then we'll discuss that it has an inverse function, which is the base 2 logarithmic function. So let's start with the graph. It is a growing exponential function. It has a y-intercept at x or y equal to 1, so at 0, 1. If I go 1 unit over, I'll double and go up to 2. If I go another unit over, I'll double and go up to 4. If I was to go 1 unit back, I'd cut it in half, and I'd have minus 1, 1/2 for that point. F is a 1-to-1 function. The reason for that is if I draw a horizontal line anywhere on the graph, it will hit it at most 1 point. As such, every output, every y value of this function has a unique corresponding input on the x-axis. For every positive number, I can find a unique real number whose input to the exponential function gives me that y value as its output. Therefore, f has an inverse function. And just descriptively here, if I take x and I plug that into the exponential function, which we're calling f, I get some y value out. Its inverse function is going to reverse the direction of this arrow. It's going to take the y now as its input, send it through the inverse function, and send it right back to x. It's this inverse function of the base 2 logarithm, of the base 2 exponential function, which is the base 2 logarithmic function. So here's our definition. The base 2 logarithm is the inverse function of my function above, of my exponential function. And its value at y, f inverse of y, has this notation for logarithms, log base 2 in this case, because that's the base I'm working with for the exponential function, of y. The key defining feature is described in this picture right here. And I'm going to re-express this little diagram in algebraic notation now. So what happened is I took 2 to the x, that was my input to the exponential function, and I got some number y out of that. This equation is true, this exponential equation here is true, if and only if the corresponding logarithmic equation involving the reverse direction is true. Now y goes into the log base 2 function, and it's going to return x back. So y is equal to 2 to the x if and only if log base 2 of y gives me x back. Observe how the input and output of this equation have been interchanged to become the output and input for this equation here. Y comes out of the exponential equation. I put that into the logarithm to find the x, in other words, to find the exponent over here. If you write anything down in this video, it's this expression right here. This is the defining quality of the base 2 logarithm. Let's do some examples. If I take 2 and I cube it, I get 8. That is an exponential equation like I've written over here on the left. The logarithmic version of this takes log base 2, because that's the base I'm working with, and it takes the output of my equation over here, the 8, and returns to me the exponent. So observe how the 3, the exponent in the exponential equation, corresponds to the output in the logarithmic equation on the right. Let's do one more. If I do 2 to the 0, remember 2 to the 0 gives me 1. that was corresponding to this point on the graph. This is an exponential equation. 1 came out of it, so I take log base 2 of 1, and the resulting answer is the exponent over here, the 0. Again, the logarithm's result, what it gives as its output, is always the exponent in the exponential equation that I started with. Let's do a couple in reverse order. I'm going to now ask to compute a logarithm. I want to find log base 2 of 1/2. I don't know what the answer of that is right now. Its answer will go in this box that I just put in here. So whatever we compute to be the answer, we'll put it in the blank there. I'm going to think about it in terms, right now I have a logarithmic expression. I'm going to think about it in terms of the corresponding exponential expression to see if that helps me answer the problem. So the base is 2. The answer I get over here, the box, is going to be the exponent over here. And what I put into the logarithm is supposed to give me the output of the exponential equation. So now I have to think about what exponent that I raised 2 to can give me 1/2. And of course the answer is -1. That's corresponding to this point on the graph here. 2 to the -1 gives me 1/2. I read that exponent of the exponential equation off, and I report that as my answer to the logarithm. Let's do a similar one. I'll take log base 2 of the square root of 2. I don't know what that answer is immediately, so I'm just going to leave it as a blank. The base is 2. The answer I get from the logarithm will be the exponent over here, and I want it to equal the square root of 2. Radicals, like square root of 2, correspond to rational, fractional exponents. A square root is a 1/2 power. I read off the exponent in the exponential equation, and I report that answer as the result for the logarithm. Here's another one. Let's take log base 2 of -4. Not sure what the answer is. So I'm going to rewrite it in exponential form. The base is 2. And I want the result of taking 2 to some exponent to be -4. I hope your alarm bells are ringing right now, because what I'm asking you to do is take an exponential function, compute its value, and get a negative number as the result. If I look at the graph of 2 to the x here, I'll see that it never actually hits a y value down here of -4. 2 to the x is greater than 0 for all real numbers. No matter what I put in here for x, I'll never equal -4 for all x. Therefore, there really is no answer here. Log base 2 of -4 is a nonsensical question. It's really just an undefined expression. What I'm really saying is -4 is not in the domain of the log base 2 function. And we can summarize that now as one of the properties of log. The domain of log base 2 of y only will allow as its inputs positive real numbers. So the domain is defined, or the logarithm is defined only for y greater than 0. That's because the outputs of the exponential function are positive values, so the inputs to the logarithm must be positive values. Let's now turn to graphing the logarithm that we've just talked about. This is a skill I would like you to have, to be able to draw the graph of an exponential function and on the same coordinate axes draw the graph of its corresponding inverse function as a logarithm. And you should be able to do this accurately and highlight some features of the graph, domain, range, and also label a few interesting points on it. So let's illustrate that with the base 2 logarithm. The first thing we're going to do is draw the exponential function. Label a few points. Each time I go over 1, I double. Go over 1 and I double. If I go back 1, I'll cut in half. Recall that whatever goes into the exponential function, the corresponding output will become the input for the log. And the value you started with for the exponential function will be the output for the log. What that means for us is that if the point 0, 1 is on the exponential function's graph, then the corresponding flipped point, whose coordinates are 1, 0, will be on the logarithm's graph. In other words, if I go over 1, I'll have an x-intercept for the graph of the log. The log base 2 of 1 gives me 0. Similarly here, if 1 goes in and 2 comes out for the exponential function, then the input will be 2, 1 for the output for the logarithm. So I'll go over 2 and up 1 unit. Notice what happens here for this point. It will be 4, 2 for the graph of the log. Notice now, just to increase the output by 1, I'm going to have to double the input now for the graph of the log. So I'm going to have to take this and double the output just to go up 1 extra unit. If I want to see the y value go up to 3, I'm going to have to double the input, and it'll be all the way out here at 8. This point here is negative 1, 1/2. That will correspond to 1/2, negative 1. So to go down 1, I had to cut the input by half. If I wanted to go down 1 more, I would have to cut it in half again to be 1/4, and I'd be down here. Keep cutting in half on the x-axis, and that will push you down 1 more unit on the y-axis. So filling in the dots, here's the graph of y equal to log base 2 of x. Recall you get that graph of the inverse function by flipping it over the graph of y equal to x, the diagonal line. The domain, as we mentioned before, of the logarithm is all positive numbers, so 0 to infinity, because that's the range of the exponential function. The range of the logarithm is all real numbers. I'll eventually get any negative number down here. I'd eventually get any positive number. I'll have to go very far out to see an arbitrarily large positive number. If I wanted to see, say, 10, I'd have to go way out to the right in order to eventually hit that value, but eventually I will. If I double my input enough times, I'll go past any value I want to hit. Recall there's a horizontal asymptote on the graph of the exponential function. That becomes a vertical asymptote on the graph of the logarithm. So there's a vertical asymptote now at x equal to 0. Finally, the exponential function grows. In fact, we call this kind of growth exponential growth after all. In this case, it's doubling for each input value, and we would kind of consider that exponential growth to be somewhat fast. Change the x-coordinate by 1, the y-coordinate will double as a result. Notice that the impact of that requires doubling the input just to change the y value by 1. That's logarithmic growth. It is growing, but I would contend that it's growing very slow. So qualitatively, I want you to think about logarithmic growth as being slow growth if you reflexively think of exponential growth as somewhat fast growth. Notice in between the two is this line y equal to x, which is linear growth. So there's some sort of hierarchy here. Exponential growth beats linear growth, but linear growth beats logarithmic growth.